I will have used information on the price of a sandwich and the weight of cats in order to modify the data I got on the temperature of the office. I'd like to tell you about what some people call the most surprising discovery in the history of statistics. So this is called Stein's paradox, and it was a discovery made by a very famous statistician called Charles Stein. Even at Stanford, which is one of these world-leading statistics departments, and always has been, he was known as the Einstein of the statistics department. So he's really held in high esteem, one of the absolute superstars. A lot of people tell this story using baseball analogies. I thought a better analogy that everyone understands is the temperature. Right? We all know what the temperature is. Let's take the problem of trying to work out what temperature it is in this office. Temperature is a real number, right? So it's hopefully positive in this office, real number. So it lives on the real line. And let's suppose it's there in this picture. And we'll use the Greek letter mu to denote the actual temperature in this office right now. For sort of reference, how does it feel to you in the office at the moment?
It feels like just lovely, just perfect, like coolish, but just nice.
So if you're going to put a degree Celsius on it, what would you say?
I would say 20 degrees Celsius.
20 degrees Celsius. Okay. So we are statisticians here, right? So we can't just guess 20, we have to do an experiment. So we've got to collect some data. So let's suppose that we've got a thermometer. And in fact, I have a thermometer that I'll get out in a second. So that thermometer is going to give us a data point, right? And that data point is going to be about mu. It's going to be about the temperature in this office, but it's going to be a bit wrong, right? Because thermometers, well, they sort of depend exactly where you place them. If your hand's too close to the heating bit, there's a lot that can go wrong, right? And actually, you've got to read the thermometer with your eyes. It's an imprecise science. The reading we get from the thermometer is going to be an approximation to this true temperature. On average, it'll be right, but it could be a bit too high, a bit too low. Let's say 1 degree either side. That's sort of a reasonable size of error to expect. Let me draw a curve here. This is going to be this very famous bell-shaped curve. We call this a normal distribution. And let's suppose that the reading we get from the thermometer follows this kind of normal distribution. So this is a probability density function. And what that means is that the reading we get from the thermometer will be somewhere proportional to the area under this curve, right? It could be just here to the left, or it could be here to the right. Let's suppose it was here, just for the sake of drawing something. And we'll call X the data that we get from the thermometer. So let's actually do it. Let's get the thermometer. So we're going to work in Celsius because we're in the UK. And it says, I'd say 18 degrees Celsius. What did you guess, Brady? You guessed 20.
I said 20. I was going to say 18 as well.
Okay, well, I'm going to be generous. I'm going to give you the opportunity to change your estimate. So this is not totally correct, right? So we just explained that, this could be a bit wrong.
Yeah.
On the basis of this data and your prior guess of 20, what would you like to revise your...
I do trust the instruments, and that has been near your computer, which is a bit warm. I'm going to say 18.2. 18.2, okay, that's interesting. So as we know, this isn't exactly right, but it's a reasonable sort of ballpark, right? It turns out that using the reading from the thermometer is a good idea in general, right? And in some sense, it's the natural thing to do. If we've got one piece of data that we think is sort of unbiased and equally likely to be bigger or smaller, reasonably close to the true temperature, this is really the best thing that you could do. And we can be precise about what that means. So let's think about how to measure the performance of the estimator that we get from reading the thermometer. Right, so this is what we do as statisticians. We think about the data, how we use that to estimate the quantities we're interested in. So you're considering that reading we took off the thermometer to be an estimate of the true temperature as well?
That's right. And it's going to give me a different value every time I do this experiment, right? Because where I put this thermometer is going to change the reading, right? If I put it near to the window, it will probably get a bit colder. If I hold it here, it's probably going to get a bit warmer. So there's some randomness associated with taking this measurement.
And we could use 100 different thermometers as well.
That's right. And this is a very cheap thermometer, right? I got this off eBay, so it's probably not particularly accurate. So let's think about how good this estimator is. So the error is going to be the difference between the measurement that we get and the true temperature. And it helps things if we square this error, right? So that's going to mean errors are positive and big numbers here are big errors. And as we've just explained, the act of reading a thermometer has this inherent randomness, right? Every time we read it, we might get a slightly different outcome. So we're going to not just look at the actual error, but we're going to take an average, right? So we're going to average over all possible instances of just using the thermometer. And the way we write down an average in statistics is with this E notation. So this E stands for expectation, and it's just a statistician's way of saying arithmetic mean average here. So this quantity here, it's got a very special name. It's a name that you may even have heard of. It's called the mean squared error, because we've got the mean, the square, and the error. So the mean squared error is a way of measuring the performance of an estimator. You'd like a mean squared error that's small. And in general, this mean squared error, it could depend on the true value of the temperature mu. It turns out that this approach of just using the thermometer in this case is optimal in a sense when it comes to mean squared error. So let me explain what that means. So I'm going to draw a little picture here where on the x-axis we've got the true value of the temperature in the office. On the y-axis we've got the mean squared error. And what you can show is that the process of using a thermometer and using the reading of the thermometer to estimate the true temperature, that will give us a mean squared error that's actually constant, independent of the true temperature in the room. So if I took this thermometer and I used it to measure the temperature in a lovely warm office somewhere in, say, Adelaide, I would get a reading that was as accurate as if I used this thermometer to take the temperature outside on a frosty April morning here in Newcastle. So the mean squared error is actually independent of the true value of the temperature mu. Right. So let's contrast that to your approach, which was the approach of balancing your prior belief that the temperature was about 20 with the reading on the thermometer, which was 18. So you said 18.2. So let's draw 18.2 on this picture. If the true office temperature was 18.2, you would have zero error, right? You would have got it absolutely spot on. But of course, as it happens, the office temperature is not exactly 18.2. We don't know what it is, but it's not, it's very unlikely to be 18.2 the same. And the error that you'll get by taking this guess of 18.2, well, it's going to be really rather big if the office temperature is far from 18.2, right? So the mean squared error has this square in it. So it's going to increase quadratically as you move away from 18.2. Yeah. So in the exceptional case that the office temperature really was close to 18.2, your approach would have been absolutely impeccable. But in general, it could have a rather large error. If your guess of 18.2 was very wrong, then you do much better by using the natural estimator of just using the data point that you get from the thermometer compared to incorporating your prior belief about what the temperature could be. There's another property of the natural approach of using the thermometer data, which is called admissibility. So what that means in a nutshell is there's nothing that you could do with this data that would always give you a better estimator. Now that sounds sort of trivial or confusing, right? Because it's so obvious. If I tell you what the thermometer says, there's nothing you can do with that information that's going to always give you a more accurate estimate of the temperature in the room, right? There's no point adding 10 to this or timesing it by 5. Using the measurement from the thermometer is, in some sense, the best thing to do, right? And that's why we say the natural estimator is admissible. So far I've not said anything surprising at all. I've just introduced some notations and definitions. So what is Stein's paradox? Okay. So to see Stein's paradox, we're going to have to go beyond one dimension, and we're going to have to think about estimating 2 or more quantities of interest, right? So let's get a fresh piece of paper.
All right, I'll get you one. Now, 2 things.
Well, maybe more than 2. Let's work in general, right? Let's say we've got a list of D things, where D is going to be a shorthand for dimension, the dimension of the vector of quantities that we are interested in estimating. So let's denote this by mu with a line underneath. It's a vector that consists of D quantities. And so perhaps the first one is the temperature in the office, but then there might be some other quantities as well. We might be talking about the average price of a sandwich in Newcastle, the average weight of a cat in Tokyo. Yeah. It could be anything. And we're going to suppose, like just in the first example, we've got a way of measuring each of these quantities that has some error associated to the measurement. And we'll assume that the errors follow this normally distributed bell-shaped curve as we did in one dimension. So our data now corresponds to D independent measurements that approximately measure these quantities of interest. And we can do everything as before. We can define the notion of mean squared error. The only thing we need to change now is when we take the difference between the true vector mu and the vector of measurements x, we need to use a norm. We need to measure the length of that error, right? Because this is now a vector, not just a number. So what we do is we take the difference between the vector of measurements and the true vector mu that we're interested in, and we take the norm of that. So that's a way of measuring the length of the vector that goes from mu to x. And we'll square that norm, and we'll take the expectation as before, and this is the D-dimensional version of the mean squared error that we saw earlier.
And is that error an error that's encompassing all the measurements, or is there a different one for each measurement? Is there one for the temperature, one for the cats, one for the sandwiches?
So this mean squared error actually bundles all of those errors together, and it measures your performance overall on this collection of D estimation tasks.
How can that be though? Because they could be so different. Like one could be something you measure really accurately with really small numbers, and one could be the size of planets and another side of the universe? Like,
right. So let's suppose that each of these measurements, so x1 is a measurement of mu1 whose error has size about 1, right? So we're going to assume what we call a standard normally distributed error. So it's equally likely to be about 1 higher, 1 lower with this characteristic bell-shaped curve. And that will be true for each of these quantities. So we assume that everything is on the right scale, meaning that the errors that you get by taking these measurements are about as big as each other. And so what's the paradox? So the paradox is, if you have this vector of measurements, x1 through xd, the natural thing would be to use this vector as an estimator for the vector mu, of mu1 through mu_d. It turns out that estimator is inadmissible. You can do uniformly better than taking the natural estimator if you're interested in minimizing the mean squared error for estimating mu. Now that seems shocking, right? Let me draw a picture that explains what I've just said. But let's suppose that mu is two-dimensional, so mu lives in this two-dimensional plane, and I'm plotting here the mean squared error as a function of mu. So this again will be constant. It turns out there's something I can do, and this is going to be true in dimension 3 or higher, that gives me a mean squared error that's uniformly lower than the mean squared error of the natural estimator. So given only these measurements, let's suppose these are temperatures in offices around the world, so given these independent readings from thermometers, there's something I can do with these data that gives me a smaller mean squared error than just using the data themselves as estimates for the temperatures in those offices. So let's unpack why that's true. So this is known as Stein's paradox. It was developed by Stein in this paper from 1956, but the idea was crystallized in collaboration with Stein's student, Willard James. And this gives rise to something called the James-Stein estimator. So I want to explain what the James-Stein estimator is and why it works. So I'm going to draw this picture in 2 dimensions, but as we said, the paradox is going to really kick in at dimension 3 and above.
it doesn't actually kick in at 2 dimensions.
It doesn't actually kick in at 2 dimensions, and the reasons are somehow technical reasons. It's 3 and above. Now, let's suppose this is the vector mu in 2 dimensions, so I can draw it on paper. And here's an origin. So we've got mu1 in this direction, mu2, and this is the thing we're trying to estimate. Now, we're going to take readings of mu1 and mu2, and under this model of a normally distributed error that's independent for the first component and independent for the second component, our reading could be, say, over here, or over here, or over here, and it's in fact equally likely to be anywhere on this circle of constant radius centered on mu, right, by the symmetry of the problem we've set up. So here's a bizarre but true statement. You're more likely to be further away from the origin when you collect your data than the true vector of quantities you're trying to estimate. So let's think about that. If I'm equally likely to be, say, over here or over here, and I draw a line from the origin to the vector mu of quantities I'm interested in estimating, well, let's consider other points that are the same distance from the origin, right? So what I'm going to do is draw a circle with this radius centered at the origin, and it will look something like this. And what you can see is that more than half of the time, my vector of measurements x is going to be further away from the origin than closer to it. And that's very strange, right? Because I've taken these independent measurements of each of the d quantities I care about. Each measurement was equally likely to be smaller or bigger than the true value. But when I collect them together into a vector, that vector is likely to be further away from the origin than the collection of quantities I'm interested in estimating. And what that means is you're going to overestimate the size of this vector mu when you just use your vector of measurements as an estimator. So Charles Stein and Willard James realized that there's something you can do here to improve on the natural estimator. And the idea has become known as shrinkage. So what I'm going to do is I'm going to take that estimator and I'm just going to pull it a little bit towards the origin, right? So here's the origin. I'm going to take that estimator and pull it just a little bit towards the origin. And in the case of this estimator here, well, in pulling it towards the origin, I've reduced the distance to mu. Right? So it's actually got closer to the vector I'm interested in estimating. That wouldn't happen for this one, right? If I pull this one towards the origin, it's going to get further away from mu. So it's not the case that pulling the vector of measurements closer to the origin always improves the estimate, but it does so more often than it doesn't. And you can see that here because more than half of this circle has been shaded in, right? It's further from the origin. This isn't a rigorous proof of anything because I've just drawn a circle and waved my hands, but this gives you 95% of the intuition for why this result's true, right? And so the James-Stein estimator is a recipe for saying how far I should shrink these vectors of measurements to the origin. And we have a formula that they propose which looks something like this. 1 minus, and then d, the dimension of the vector of things I'm interested in, minus 2, all divided by the length of the vector of measurements squared, all multiplied by the vector of measurements. So let's unpack this formula a little bit. This is the vector of my measurements. And if I didn't have this factor here, this would just be using the data to estimate mu. That's the natural thing to do, right? But this factor changes things. This says that because this term is always less than 1, I'm going to be pulling things towards the origin by some amount. That amount will depend on the dimension, d. So in high dimensions, this thing will be pulled more strongly towards the origin. And it will depend on how far I am from the origin in the first place. And that's what the length of this vector x signifies here. So you can prove that the James-Stein estimator always has a lower mean squared error than the natural estimator if and only if the dimension d is greater than or equal to 3. Right? So that's when Stein's paradox kicks in and we can do something better than just using the vector of measurements to estimate the vector of quantities of interest mu.
So you're telling me if I delivered you all this data about the temperature in rooms, the weight of the cats in Tokyo, the prices of the sandwiches in Newcastle, and I said, how close are these to being true? You would apply this little weighting to all that data to get a better result than what I just delivered you as raw data.
Exactly. And what's really paradoxical about that is that I will have used information on the price of a sandwich and the weight of cats in order to modify the data I got on the temperature of the office to get a better estimate.
That is amazing.
That's bizarre, isn't it? And that's why this result was so shocking. It's known as the most surprising discovery in statistics for a very good reason. It doesn't make sense, right? But as with all paradoxes, there is some explanation, right? So the explanation for why this can occur is that we're measuring the error of the vector here from the vector of true quantities of interest, right? So we're actually coupling these independent estimation problems together through a common objective. And that's the reason why the James-Stein estimator actually leverages information on each of the different quantities we're interested in to decide how much shrinkage to apply.
Does the validity of this method depend on how the data was collected? Like if all that data about the cats in Japan and the sandwiches and the temperatures was collected by just Brady having a guess, would this method still work? Or does it have to have been collected in some more valid way, like with a thermometer or with official government statistics and things?
So the James-Stein paradox relies on having unbiased estimates of each of the quantities, and to some extent it relies on having this idea of a normally distributed error. But actually the normal distribution part of this isn't totally critical. And you can see that here, right? So the circle that I drew here, it would have been a perfect circle if we really had normally distributed errors. You can see more than half of the circle is further away from the origin than is closer. And that shows you that actually there is some departure from normality that can be tolerated within the James-Stein paradox.
Is this now standard practice for statisticians when they're figuring stuff out? Is this like just an everyday method?
It actually is in a sense. So as I said, this paradox was published in 1956 and we're now 70 years down the line. I guess I should say 69, let's be precise, it's on a maths podcast. So what we do is we have a more refined understanding of shrinkage. Okay. So let's take an example from modern machine learning. In machine learning, you're interested in predicting some quantity of interest, right? You might be classifying dogs and cats. And the way that you do this is you build a neural network which consists of often millions or billions of parameters which have to be estimated somehow. So in the analogy here, mu would be the vector of parameters of your neural network, and these are not observed directly, right? You can't just measure parameters of a fitted neural network. You have to learn what they are. So what you do is you try out different configurations of parameters and you see how well your neural network performs at the task, maybe classifying cats and dogs, and then you tune them in order to get better performance. And so although the process of relating the data on cats and dogs to the neural network parameters is now indirect, this idea of shrinkage is absolutely essential in getting these things to work, right? So one thing that you can do, and is done in machine learning, is just to take your vector of estimated neural network parameters and shrink it to the origin. Right? So although the observation process relating data to parameters is indirect, this idea of just shrinking the estimated parameter to the origin is in fact a very powerful and widely used idea, even in modern machine learning. We've got much more complex and sophisticated things that we do with shrinkage as well. To give you one example, there's a notion called dropout. And what that means is you randomly set components of your estimated parameter vector to 0, right? So that's going to pull it towards the origin as well in a more indirect way, right? So it's slightly strange, but even that kind of shrinkage has a powerful empirical effect of improving the performance of modern machine learning methods. What would have happened if we'd done this experiment in Fahrenheit instead of Celsius, right? So what that means is that the origin changes, right?
Chris is just one of several Numberphile contributors who also happens to be a recipient of a Philip Leverhulme Prize. These prestigious grants are awarded by the Leverhulme Trust, and one of the Trust's main purposes is supporting blue skies research, seeking breakthroughs which will hopefully benefit society, but maybe in less obvious or unexpected ways. It's an independent charity that's been running for over 100 years. Do check out their website for loads more information about how they work, who they support, even how to apply for funding yourself perhaps. I'll include all the links below in the usual places. Our thanks to the Leverhulme Trust for everything it does to push research forward, but also for making this video possible.
Or if I had some prior idea what sort of temperatures might be, right, and I choose my origin appropriately, then the picture would look much more like this. So when I draw my circle now, you can see a much larger proportion of the states are further away from the origin than closer.